Okay, so I'm making this video to make up for the fact that we're missing class yet again for the snow. And we're finished chapter 1 now and starting chapter 2. And like I've said in class multiple times, there's kind of a logical progression to what we do, where we essentially redo everything you've done for all the math you've done since like middle school and just kind of add another layer to it. So in chapter 1, we talked about points and we talked about lines in space and talked about making things parallel and perpendicular, although we had to define things in terms of vectors. So then we talked about parallel vectors and parallel lines and perpendicular lines, but then in terms of vectors, we said they were orthogonal. But again, there's this kind of idea that our use of vectors allows us to relook at everything we've already done in math before. And again, harkening back to middle school or whatever, you learn about points and distance formula and all of that. Then you learn about lines and parallel lines and perpendicular lines. And then essentially you say, okay, I have done everything with linear equations that I can do. So how do I make things new and different? You make things quadratic. And you start solving quadratic equations. And then you start solving cubics and quartics and polynomials in general. And essentially, something that is linear and straight, you tend to then start making curvy and polynomial in nature. And yes, I'm aware that ultimately you can have things that are differentiable and kind of curvy versus things that are non-differentiable, where you have points like, say, in the absolute value function. And we'll have to kind of look at that. But essentially, we want to say, okay, I can have a line in space, and now I have a way to define it. Give me a point, give me a direction vector, I'm good to go. I can define a plane in space, give me a point, give me a normal vector, and everything is straight and linear, even though it's a plane in 3 dimensions, all the variables are linear. What happens if instead of my thing being linear, it's more curvy? How do I deal with that and how do I define it? We've mentioned this in class before a few times. And for right now, we're not actually going to worry about, say, surfaces and things like that in space. That takes a little bit more work. We're essentially going to take our line and kind of make it a curve in space. So, if you will, maybe I'll have something like, just to draw over here, something like that in space. Kind of like a spring right there, or a helix in mathy speak. And the question is, how in the world do I define that? Like, if it's flat in 2 dimensions, it's not even a function, but I could try to come up with an equation to define it, although I'm not really sure how to do that. But now again, suppose that's 3-dimensional in space like this, how exactly do I come up with a way to describe that? And we understand now that vectors seem to be very useful, so we're going to use vectors to try to define that thing. In order to do that, we need a new definition, what's called a vector valued function. Or for the purposes of essentially the entire rest of the semester when I have to write this, VVF for vector valued function, because I get tired of writing vector valued function out long form every single time. And we're going to be writing this a lot because these will be really, really useful to us. And as far as it goes, the way we'll define them, in order to keep this video somewhat short, because I know you people are going to watch it if it's like an hour and a half long, so to kind of make this somewhat brief with descriptions here and all that today, we can just define our vector valued function as f of t equals p of t, q of t, r of t. We're essentially, f of t is a vector. I have each of these component functions of the variable t, variable, parameter, whatever you want to call it, p, q, and r. And if I sketch this, it's 3-dimensional. F of t, I need a different color. F of t is a vector, so say maybe for the purposes of this, we can define our functions in a minute. I get that vector right there. That color is showing up. Not that great. Okay. I get this vector right here. Then I pick a different t, and I get maybe that vector right there. I pick a different t, and I get that vector right there. Then we look at the terminal points of those vectors, and that gives me my curve right there. So in theory, if I had that curve right there, maybe if I draw a quick x, y, z axis, let's see. We'll do that up to my ability to draw this reasonably well. Maybe something like that. Then I can try to define a vector valued function where I'll have a vector that terminates there, and a vector that terminates there, and a vector that terminates there, a vector that terminates there, etc., etc., etc. And now I can see that if I can do this, then yeah, I can actually sketch out curves in space. I just need to come up with the functions p, q, and r that will give me those vectors for different values of t, so I can get that curve right there. And that's kind of the goal of this chapter. As it turns out, this shape right here, this circular helix, is fundamentally important. And in the same way that, say, when you start talking about functions that are nonlinear, you have polynomials, but you kind of memorize the quadratic, the cubic, the absolute value, the square root, the cube root. You can have the reciprocal function. You can even use the greatest integer function. And you kind of memorize certain functions, so you just recognize them, exponential functions. And then when you see a graph, you can kind of take the basic function you know and expand on it, transform it to get a new function. Kind of the same idea here, where this is ultimately going to be our basic function. We'll spend a lot of chapter 2, yeah, we're in chapter 2, working on that particular curve right there, that particular vector valued function, and we'll use that to describe pretty much all the vector valued functions we want to look at. So we're going to use this a lot. We're not going to define a lot of it today. We'll expand on it in the next section on Monday, assuming we have class, even though it'll be like 60 degrees. Anyway, okay. But the idea, at least for today, we want to just look at this vector valued function and get an idea of how it works. So for the purpose of this, here, I marked the board, so I should be able to stay within it. Suppose I have f of t equals e to the t, t plus 1, and t squared minus 3. Then I have 3 component functions, p of t, q of t, r of t. For any value of t, I plug t into each of those. That gives me a vector, and I'm good to go. So if I have, say, f of 0, I get e to the 0, which is 1, 0 plus 1, which is 1, 0 squared minus 3. Plot that vector, and then the terminal point, 1, 1, negative 3, is the point on my curve for t equal to 0. Pick different t values, get different vectors, plot their terminal points, connect the dots, get my curve. But in the same way that once we kind of defined vectors and defined operations on them, we had to check to make sure things like distributed properties and associative properties and all that held. The same idea here. Now that I'm defining a vector valued function, I want to kind of run through all the math I know and make sure it still works the same. We know all the properties of vectors now. I know this is defined in terms of a vector, so I know my properties, dot products, cross products if necessary, scalar multiplication, all of that will apply here. I just need to see my properties of functions and see how they work. So first off, you define a function, you care about the domain and the range. But for the purposes of this, the idea should be pretty obvious. To get the domain of, say, f of t, I look at each of the component functions and I look at their domain. If there's anything that isn't included in any of those domains, then it can't be included in the domain for the whole vector valued function. So for the purposes of this, e to the t is defined everywhere. That's a line defined everywhere. That's a quadratic defined everywhere. All of these are defined everywhere, so my domain is all real numbers. If I altered this and maybe I'll do this over t minus 2, then this isn't defined for t equals 2, which means the whole vector valued function isn't defined for t equals 2. which is an obvious way to define it. I'll also point out, and I've mentioned this before in class, if there are parts of, say, pre-calc, trig, and in this chapter, we'll get into the kind of Calc 1 and Calc 2 stuff. If there are parts of that you really enjoyed, that's great, because you're just really going to do everything in triplicate. So you get to do the things you enjoy in triplicate. If there are parts of that you didn't enjoy, if there are derivatives and integrals you didn't enjoy, I'm sorry, you're going to get a lot of practice with it because you're going to have to do it in triplicate. But essentially all it really means is a lot of our basic definitions will just have to be true for all three component functions, and that will tell us what I want for the whole vector value function. I want to get this out of the way. Okay, good. And same idea for the range. I can look at the range of all three of those to get an idea of the range of my vector value function. That's not that big of a deal. But like I said, now we can kind of start looking at calculus. And I think the first thing you do in calculus is you talk about limits and continuity. So for the purposes of this, again, I'm not going to write the big formal definition out because you people would just fast forward through it anyway. And the understanding is what we really care about. We're going to do one formal proof that I'll sketch out here in a few minutes. But if I have a vector valued function and I want to find the limit at a point, I just write the limit as t approaches t sub 0 of f of t is equal to L. The exact same notation as Calc 1, except that instead of a function and a limit L scalar, now these are vectors. But L, the vector, is equal to L sub 1, L sub 2, L sub 3. And in order for this limit to exist, it only exists if the limit as t approaches t sub 0 of p of t is equal to L sub 1, the limit as t approaches t sub 0 of q of t equals L sub 2, and the limit as t approaches t sub 0 of r of t equals L sub 3. So again, essentially this idea of doing things in triplicate where the only way the limit of my vector valued function exists is if the limit of each of the component functions exists, which just means I have to find the limit in 3 times. And I will point out, and we've mentioned this in class before, I don't necessarily have a rule to calculate the limit of a vector function, but since I define the limit in terms of L, which is defined in terms of each of the component functions, each of the component functions is real valued functions, so these are just regular limits of single variable functions. Those limits I know how to calculate, whether I choose to do them algebraically or using L'Hopital's rule if they're differentiable. So essentially I do all the rules for limits and all the calculation of limits that I knew how to do or know how to do from Calc 1 and maybe Calc 2 based on when you did L'Hopital. I just have to do them in triplicate. And essentially either the limit will exist for all 3 component functions, so then the limit exists for the vector valued function. If it doesn't exist for one of them, then it doesn't exist for the vector valued function. Let's see. I'm limited on the amount of space I have to write. And I will point out, we will expand on this, I'll leave that here. We will expand on this more in class. Like I said, you're still preparing for your first exam, so this is more a brief overview of what we're going to cover, and then we're going to expand on it throughout chapter 2 as we look at that right there. But once you have limits, then you talk about continuity. But we've already said in class, as far as continuity goes, for a single variable function, the definition of continuity that you got in Calc 1 was that, this is the thing I mentioned in class if we were meeting, that I was going to ask you again in about 2 weeks. We mentioned this on day 1, and see if you still remembered. But let's see. Now we're not in class, so I can't do that. There are 3 properties that have to be true for a function to be continuous. The limit has to exist at the point. The function has to be defined at the point, and the value of the function at the point has to be the value of the limit at the point, which is the third condition, which is the really important one. And if all three conditions hold, in particular the third one, then the function is continuous at the point. But now I know I talk about, say, limits of my vector valued function in terms of the limits of each of the component functions, which then means if I want to talk about continuity of a vector valued function, I talk about continuity in terms of the limits and the function being defined there at each point, but then I can simply find the limit of each component function, and if those limits exist, and they equal the value of the function for each of the t's at those for each of the component functions at that point, then the vector valued function will be continuous at the point. So again, it's the exact same definition as our single variable functions. We just do it in triplicate once for each of the component functions. And one thing based on past experience that I would stress that I think tends to cause confusion, occasionally students will say, solve this out and find out that we'll say r of t, the limit doesn't exist at 0. But then they just kind of discount that, find the limits here and here, and say the limit exists, and it's pretty much an all or nothing thing. All three exist, and you have your limit. If one does not exist, then the limit does not exist. Same idea with continuity, same idea with domain. If there's a problem in Q of t, then there's a problem for the whole thing at whatever value of t causes the issue. So just keep that in mind. That is based on past experience. That's one thing that I think tends to kind of confuse students. But once we have limits of continuity, the next kind of logical step is to combine them and to get your derivative. And I reiterate, because you should all know this, but we've established in class so far that maybe you don't necessarily know it. The actual definition of the derivative for a single variable function, d dx of f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And then I understand that the vector valued function is different than the single variable function, but I defined this in terms of the component functions, so can I just kind of take this definition and expand on it? Since the limit is defined in terms of each of the component functions and continuity is defined that way, it would seem logical that if I want to take the derivative of a vector valued function, I should take the derivative of each of those. So the kind of logical expansion of this is to say the derivative d dt, since we're using t not x, of f of t is equal to the limit as h approaches 0 of, let's see, I want to use the book's notation, yeah, good, of f of t plus h minus f of t all over h. And here, I just rewrote the definition in terms of the limit, but again, instead of having the single variable function f, I'm using the vector valued function, also f. But then, how do I actually calculate that? Well, I actually understand, again, since this is a vector valued function, I know my properties of vectors. Addition of vectors like this, and subtraction, is defined easily, not a big deal. Division, which is in this case, since h is a scalar, just scalar multiplication, that's well defined, which means this does actually make sense. If I had some vector valued function f of t, I could find f of t plus h, plugging into each of the component functions. I could find f of t, I could subtract them, you subtract the vectors component-wise. I could divide by h, which is again, just scalar multiplication by 1 over h. So this is definitely well defined, but again, the kind of logical way of thinking about it is, if I want to get the derivative of this, I should just take the derivative of each of those. And I just want to quickly sketch this proof out. I've mentioned it in class before. One of the things we have to do in math is kind of redefine everything. Math is really about the definitions and understanding them. And can I use my understanding of the definitions of vector valued functions and component functions and the derivative, and show that the derivative of this is just the derivative of each of those. And the proof is not that hard. We can just sketch it out really fast. And again, I do point out, there is the big formal theorem in your textbook. Here we're just going to sketch it really fast. And assuming we have a vector value function and continuous component functions, then just to make sure I use the same notation as your book, the derivative of f with respect to t of t is equal to the derivative of p with respect to t of t not minus. The derivative of q with respect to t of t, and the derivative of r with respect to t of t. And again, the idea, the derivative of the vector value function is the derivative of each of those. Can I show that's true? And similar to one of the proofs we've done in class and the ones I've had you do for homework, or at least I've asked you to do for homework because it's beneficial, can you use your understanding of the properties to show that? And we're just going to sketch it out, so it only takes a few lines. I know by the definition that I had right here that I had to erase so I would have room. ddf of d of t is equal to the limit as h approaches 0 of f of t plus h minus f of t, that's a terrible t, over h. And now, how do I get to that? Well, first off, I know I'm taking the limit of all of that, but this is just, again, scalar multiplication by those two vectors. That's subtraction of two vectors. So I can separate that and separate the h. And I get the limit as h approaches 0 of, well, maybe put this in parentheses, f of t plus h over h minus f of t over h. And one thing I'll point out before we actually start doing this, I'm aware that to a certain extent, and we've mentioned this in class, it's kind of obvious as we go through this, we'll see. Well, that's just trivial, and I can just jump from this all the way to that. Mathematically, you have to actually show it out using the properties you know. I know that difference of vectors, I can separate them, and I know that this is just scalar multiplication. I know it's division, but same. So I can do the scalar multiplication by this, scalar multiplication by that, separate the difference, and then work with each vector individually. But now, I can take the limit as h approaches 0. Now, I'm going to work with each of those vectors because I know these vectors are defined in terms of my component functions p, q, and r. So, this now becomes the vector p of t plus h, q of t plus h, r of t plus h. All of that, we'll write it this way, times 1 over h, scalar multiplication. I could bring that in right now. I'm just not going to. We'll separate it by one step. Then I have this minus, same idea, that's f of t, which is p of t, q of t, r of t, times 1 over h. But now scalar multiplication says I can bring the 1 over h in and multiply each of the components. So I get the limit as h approaches 0 of p of t plus h over h, q of t plus h over h, r of t plus h over h. Then this is minus, do the same thing, p of t over h, q of t over h, r of t over h. But now, these are just difference of two vectors. So now I know to subtract vectors, I subtract component-wise, which means I can combine them and I get the limit as h approaches 0 of, let's see, p of t plus h over h minus p of t over h. So I can write that as one difference over h. Same thing for q and r. So q of t plus h minus q of t over h. R of t plus h minus r of t over h. But now, I know to take the limit of this vector valued function, I just bring the limit into each of the component functions. We already said that. So then I'm going to run out of room. But it means this becomes the limit as h approaches 0 of p of, I don't need all the parentheses, p of t plus h minus p of t over h. The limit as h approaches 0 of q of t plus h minus q of t over h, and the limit as h approaches 0 of r of t plus h minus r of t over h. But now these are single variable functions. The limit as h approaches 0 of that is by definition the derivative of p with respect to t. That limit is a derivative of q with respect to t. That limit is a derivative of r with respect to t. Which is exactly what we wanted to show. And again, as I've said before, I'm aware that to a certain extent this is somewhat trivial and kind of redundant, and you're occasionally left with, why in the world do people bother actually writing down and doing that? It's because from a math perspective, we have to take what we know, properties of single variable functions, and see how they expand to, in this case, a vector valued function in 3 dimensions. And as it turns out, it works the way it should because of the way we define vectors and their operations, and the way we define scalar multiplication and addition and subtraction of vectors and all of that. And we've seen that sometimes some of the operations we do expand nicely, other times they don't. That's why we had to use different ways to define lines and planes. And the same idea here. It looks like we have a way to define limits and derivatives of vector valued functions. You just do them component-wise. I'm going to leave off here, but I would encourage you, if you're so inclined, if you wanted to take the integral of a vector valued function, the logical assumption is you should take the integral component-wise. The integral of f is the integral of p, the integral of q, the integral of r. It works out logically. Feel free to take the time and try to sketch out the proof on your own. But we have these basic properties now and these basic operations, limits, derivatives, integrals. Now, like I said, the goal is to take that and ultimately use it to look at that circular helix that I had drawn here and other things and see what I can figure out about them. If you think about it from a calculus perspective, one of the reasons we talk about derivatives is I can use my derivative to understand the shape of a curve, figure out where it's increasing, decreasing, maximums, minimums, and all of that. Curve sketching, that chapter in Calc 1 that everybody either loves or absolutely hates. Same idea here. If I want to define a curve, say I think about that circular helix, then from a math perspective, I care about, in this case, it's always increasing, but when does it increase? How does it increase? Does it speed up, slow down? Things like that. And for different curves, I get the same thing. Calc 1 tells me derivatives and limits are a good way to figure that out. Now I have a way to define derivatives for vector valued functions, which I can use to describe those curves. So now I can see if I can expand on my understanding of derivatives and how we use them in Calc 1 to figure out how to look at the shape of the curves I now have in space. One thing I will point out that I always say is a caveat at the beginning of chapter 2, and I'll stress this in class a lot on the off chance you don't actually get all the way to the end of this video. This chapter is very algebra intensive. I know all of Calc 3 is, but this chapter is really algebra intensive. Like, some of the stuff we do won't fit on like this whole whiteboard here, even the parts you can't see. And you can occasionally, as a student, lose the forest for the trees because you're just scribbling out so much algebra. So try to keep in mind what the ultimate goal is as we go through this, and I'll do my best to kind of explain that at the beginning of class each time, so that you don't lose the forest for the trees and understand why we're doing all the algebra, because if you understand why you're doing it, a lot of times it makes it easier to see all the weird stuff we're going to talk about. And if there are any questions, if you need more examples, like usual, let me know and I'll just make more videos.